Yeah, perfect. Thank you, Hanno. Okay, well, welcome everybody. Super humbled and honored to be hosting the opening keynote for your AI Search Week. I think it's tremendous that your team is offering such an opportunity to you all. So I think Personio has always been a great employer, but I think you're shining on this one yet again. And yeah, as Hanno said, we know each other for quite some time. So I know Personio already since its very early days, when your website was still looking like this, right? This is from 2015. And it was, as Hanno said, you were riding that first wave of the last platform shift, which is the cloud. And we're, of course, now, since you're rebranding in the AI age, also officially, with you being the intelligent HR platform. 10 years ago, in 2015, I, as Hanno said, set my foot on the ground at Stanford, which was at that time, there was already that gravitational force where when you know coding and math, there was just no escaping of learning about machine learning. So kind of the wave of AI before this wave. And I picked up my old Stanford syllabus from the famous CS229 course about machine learning. And yeah, you can't make this up. It was held in the NVIDIA auditorium, which of course at that time, NVIDIA was still a graphics chip company and not the AI company. And my professor at the time, Andrew Ng, is by now also a well-known figure in the industry. And there was this one quote that he brought up in the beginning of the lecture that has stuck with me and was also the kind of naming ignition moment for Luminovo, where he said, AI is the new electricity. So what does that mean? He said, well, if you think back, the electricity really transformed every single industry over the last 100 years. There's no industry today that's working without electricity. And he really can't think about any industry that will not be equally transformed by AI. And I think that's like a metaphor that stuck with me. At that time, it was maybe still controversial, but I think today we can really feel it. It's infusing in our lives and gets into every single industry. But what I also like about this analogy is that if you really look around and ask yourself in the room, who really knows how electricity works at the bare atom level? Not that many, I guess. But we all learned how to work with it, right? How to use it safely, to not put like metal things in the fuse box and teach it to the old small kids. But we learned how to make use of it and not be scared of it, but make it transform our lives for the better. And I think that should potentially be the spirit of this week, right? How can we, as Hanno said, not be scared too much, but excited about the technology and make it use, if you're an engineer or like someone in customer support, make it work for you and for your use case. And I always like to get a little bit of an understanding about a new technology, where are we coming from and where we're going. So how I'm going to structure this talk for you today as the opening is give you a little bit of context. How did we arrive where we're at right now with this current AI wave? Then looking under the hood of these LLMs, what are they actually? How can you think about them? And then a small outlook on where things are going. And I think that's going to be then continued at the expert panel on, I think, Wednesday. All right, so let's get started. How did we get here? That's going to take us now from AI to LLMs. The main problem with AI has always been the so-called AI effect. That means people always thought AI is whatever is not possible today. So if something's done already, it's kind of software, it's algorithms, it's automated. But AI has to be something else, right? It's this kind of big carrot stick that we've always been chasing. But in general, AI is a fairly broad concept and has been around since the 50s. That's when the term was originally born. But I would say the four key moments potentially that had made it to public appearance are those four. Basically bringing us from the 1970, the AI 1.0 wave, we'll talk more about that, is when IBM's Deep Blue for the first time beat the human champion in chess, Garry Kasparov at the time. There was a big public moment at the time because before computer systems were not able to really compete competitively in chess. And this stream of more complex games continued, right? In 2011, we had IBM Watson beat the two champions in Jeopardy, which is a US quiz show. And then in 2016, we had like Lee Sedol, the champion in the more in the Asian community, well-known game of Go, which was beat by the tool that was created by DeepMind's AlphaGo. And then we escaped the game trajectory. We came to 2020, as you all know, kind of the ChatGPT moment when like AI for the first time got in the hands of the end users and people could start playing with it. And these 4 moments kind of resemble a little bit kind of 4 technology shifts that we have seen in AI. And I would love you to take away to get a little bit of a sense of all these buzzwords. Hanno mentioned machine learning before. We talked about LLMs. How can you fit them all together to give us a bit of a foundation? So AI in general is a fairly broad term, right? The book definition is it's a system that's capable of performing a task that would require traditionally some form of human intelligence or decision making. So the question about is this AI or not is not really asking the question how you do it, but what problem are you solving? This is like a box, right? And there's a machine, you throw a problem in, a solution comes out, and that problem is somehow not trivial to you. It requires some form of human intelligence. The system that's capable of doing that is an AI system. And that's in a sense, if you think about it, how this machine that was beating Kasparov at the time was also built, right? It was an AI system. It could play chess like superhuman compared to what we can all do. But how it was built was as an expert system. That means some experts sat down and handcrafted a lot of rules that were able to play then chess. And this is like the polar opposite to this other wave that we've been talking about, which is called machine learning. And to put that a little bit into context for you, so maybe you think about how we humans observe the world when we try to learn. It's probably we're observing something, our brain somehow internalizes rules, and then we act on them. And that's a little bit how computer programming has been, right? We look at data, we try to somehow write down rules, like a modeling some state of the world, something a computer program should do, and then the computer program is doing that thing. And machine learning as a concept now has had some fundamental changes to this. The change here is that we, as the programmers, we're not writing the code that's then used to solve the problem, but we are kind of writing code that is supposed to train the model. So it's basically a guiding principle of how you should look at a program, how can you continuously optimize some function, some error rate, and then that spits out a set of parameters, which is then called the model. And this is then the code that's used to solve the problem, right? So in the expert system world, we are writing the rules that are then executed. In the machine learning world, we are writing a program that's then trying to create a program that's then used. And that's the big change that we had here. So from this AI first wave, really beating chess, to the second wave now that was able to beat Jeopardy. And for Jeopardy, you could not think about every question that was out there in the books, right? You had to find some way of a machine to be able to understand language, query like something from the database, and then bring you back an answer. The next wave that was created was the so-called deep learning wave, and that's right about the time when I was at Stanford. Deep learning is just now another subset of machine learning, and the big change here is now just the selection of the algorithms we're using. So in this case, we're not using some stochastic models that we might know from our stats classes, like linear regression or classification algorithms, but we are using deep neural networks. And neural networks is, in a sense, a family of algorithms that are loosely inspired by our brain, by how our brain kind of connects neurons together to create a result. That was the kind of idea of these deep learning algorithms. What was the big unlock here? We were for the first time now able to look at data that's not just structured in tables or numeric, but something that's unstructured, like images, like text. And that's, as you can imagine, was necessary to get to the point where we are today, where ChatGPT can just read any text in the book. One technical thing that I want you to take away is like how these systems are learning. And I think there are 3 types of learning paradigms that you should take away with, how we can teach these systems to progressively become better. One is the concept of supervised learning. So what does that mean? Here on the side, you see an image, in this case, of a cat. But it's not, it doesn't have to be just the cat, how we can think about this image, right? I could also think about this image of it being an animal, it being outside, it being green, it having a color. So we humans are assigning a label to this data point, in this case, the image of a cat. And if I'm now trying to teach a model to do kind of cat classification, I basically feed it a lot of images of cats and maybe dogs and other animals, and it tries to learn that association, looking at pixels and then getting to that result. That's kind of supervised learning. Supervision comes from us humans. We assign meaning to a data object that then can train a system that then can be used. The big difference in the middle now is what's called self-supervised learning. So self-supervised means that the supervision is not coming from us humans associating something to a data point, but it comes from the data itself. In the image here, you can think about me having this image of a cat, and I can just cut out a certain part of the image. And now I can tell the system to learn from all the pixels around here, can you predict the pixels that are in the middle? And I know the ground truth, right, because I have just taken it away and hidden it from the model. And the idea is if I do that a lot of times, the system will somehow start to understand, okay, if there's one ear of the cat here, there might be a second ear, right? And try to infer these pixels. That's the idea of self-supervised learning. You can do that with text and images. And the third learning concept is so-called reinforcement learning. It's in a sense a little bit how probably we are teaching our like dogs, right? If like I'm throwing a stick, the dog catches it, comes back, and I give them a goodie or a treat, they kind of know that something, what of the thing they just did was good. It gave me a reward. So I can reward positive behavior, I can penalize negative behavior. And that's in a sense also how you can teach a system, right? Is a system successful or not successful? And that signal can then be, of course, fed back into a model to then improve itself. As you can see here, of course, every game-playing system that you had was very much built on reinforcement learning. What's the interesting catch here is that this reinforcement learning concept allows you to like not just tell for example, the dog, this is exactly how you have to run to get the stick and come back to get that reward, but I'm just rewarding the end goal. But the dog can run like this, it doesn't really matter. So I can incentivize creative behavior if it just creates the right result. In the other supervised fashions, I'm just trying to imitate a behavior. That's going to be important later on. So these three learning concepts is something that you should keep in mind. All right. Now we're getting to these last waves, to the wave we're currently in, where we just said, okay, deep learning, all these neural networks that we can train. Before we had this platform shift we are today, we had to train every single neural network purposefully on one task. We just looked at classifying cats and dogs, or playing a game of Go, or playing a game of Pong. But the big change we're now seeing is with foundation models. And foundation model is just, again, another subset. It's a model that's so big and so powerful that it basically can be a building block for everything that's downstream. It can be foundational. And that's why you see here LXM, so it can be a large language model, vision model, whatever it is, but a base model for any other task. So on the left side, you see, this is how it used to be, right? If I wanted to create a model that does text generation or summarization or question answering, it was one model at the time, one task, one model at the time. And we are all not realizing this when we're using ChatGPT, but what we are kind of doing is we're just asking the model, now you should be a text summarizer. Now you should be a question answering model. And in the time, 2015, 16, when we were building the first deep learning models on language, this was all a specific model. And now you can see with these foundation models, we train these huge things once, and then we can adapt them on the fly. And that's extremely powerful and democratizing. So just if you think about these models that we had, right? DeepL was the best for translation. At the time, Rasa was the framework for developers to build chatbots. GitHub Copilot before these new coding agents came, all very specific models. And by now, kind of ChatGPT can do all of those things. It can translate, it can do a chat, it can do coding. So that's, I think, very foundational to understand what privilege we are on, right? We're standing on these shoulders of giants of these big models that we can just use for our own use cases. Now, most of the time, we're not just talking about large X models, we're talking about language models. So what is actually a language model? You've been all using language models for probably the last years already, because the easiest language model for you is in your phone. Right? If you're starting to type on your phone, so are you, your iPhone, Android phone is proposing the next word to you. What's most likely to come after that word? being it here guy, still, or going. And that problem, predicting the next word, given everything you've seen before, that's language modeling. That's how these systems are built. Now, the big difference is that thinking back to our idea of self-supervised learning, we do have quite a lot of consistent text on the internet. So what if we take this language modeling task and just scale it? Just keep scaling it to the whole internet. And that's exactly how the current foundation models, these language models we're using, are built, right? There's the whole internet, and they're playing the game of next word prediction at scale for trillions and trillions of words. And the result of it is something how you can think about these base language models that are falling out of this are kind of a lossy compression of the internet, like a zip file. The whole internet in a zip file, like not in trillions of data points, but maybe in like a few gigabytes. What these things are kind of internet document simulators, right? So we can start dreaming up stuff on the internet. Not more, not less. Of course, at some point, you can keep scaling and scaling it. This becomes kind of costly. So ideally, you should know that this is actually not diminishing returns, but it leads to something. And that was the big breakthrough that OpenAI found in 2020. They did quite some experiments, and they found out that if we are scaling the amount of compute we're putting into a model, at the same time as we're scaling the data set and the parameters, we're getting predictively better performance. And you can see here like these small blue lines were basically always when like they tried it with a smaller model, it was better, and then it was plateauing. But whenever they took a bigger model and scaling other things, they could continuously get better performance, almost like a law. That's why they call it a scaling law. And that's, of course, when they realized, crazy. So it seems like if I just keep throwing millions and billions of dollars on it, I'm getting progressively better performance. It's almost a rule of law, rule of nature. So that's when the AI arms race started. People just kept throwing more compute at it. And the even more interesting thing that happened is, remember, we're still just doing next word prediction, right? We're just getting better at predicting the next word. But while we were doing that, new properties start to magically emerge. So in the beginning, we were just maybe good here in question answering. And out of a sudden, at 62 billion parameters, the model could summarize or could translate. We didn't teach it. We're still just predicting the next word, but all these cool new skills started to emerge. And it's interesting, I just became a father 9 months ago, and it's just interesting to observe this also with my child, right? I'm not changing anything about the way I'm talking to the child or I'm educating the child, but like last week, it started to do blah, blah, blah. So just apparently some neurons clicked and it started to emerge, this new skill emerged. And this is exactly what we see in these models. Like with more scale, magically new properties emerge. And of course, that was even more confidence and evidence that we should just keep throwing more compute at it. So that's like a line you can see this from GPT-3 to GPT-4 to Gemini Ultra. People are just throwing more and more data on it. And there seems to be no limit just yet. The returns are not yet diminishing. And of course, the one company who's loving this the most is NVIDIA. Because yeah, you see that their profits in data centers have just been exploding. All right, so that basically is the first block, right? So you should now know all the AI, machine learning, deep learning, LLMs, and what brought us here. But now we can really focus on the things that really matter in AI today. I already talked to Hanno before today. Most of the stuff I learned at Stanford is kind of obsolete because you guys are fortunate enough, you can now directly jump on the LLM train and reap these benefits and work with those systems. But how do these things actually work? And I think understanding some little bit of the context will really help you doing better prompt engineering later on and work with those systems. So this journey is going to take you from tokens to agents. So first of all, LLMs don't think in words, right? They think in tokens. What does that mean? So if you look at on the left side, you see this context that I'm holding a keynote at Personio today. That's the text that we humans consume. We think in words. The first thing that the AI system does, it's breaking down the sentence in chunks. And a chunk is a token. You can see sometimes a token is a full word, sometimes it's like a fraction of a word. And to us, this sometimes looks a little bit like weird, right? For example, if you see the I in the beginning of a sentence and the I with a space before are two different tokens, right? You see in the tokenizer, there's just a number. So this one is like 40 and the other is 356, 57. So that's how the first thing that the LLM does, it breaks it down into these tokens, and then every token has like a representation in numbers in a vector space. This is something we as humans can't comprehend anymore. But this was important for this. That's why these tools suck at some things like word counting traditionally, right? Because it's not thinking in words, it's thinking in tokens. That's why it also sucks in thinking about how many R's are in strawberry. That's a famous example where it always failed because it's thinking in tokens. So I think that's always just important to you to understand this is how they think, and that's why they make sometimes stupid mistakes that we humans think they are just should come natural. What's also important, these base models are pure language models. So remember, I told you that they are internet document simulators. They dream up internet stuff. So I actually went out. You can't almost get that anymore, but there is like a place where I went to access a base model. It's a big base model. It's the Llama 3.1, 450 billion parameter base model. And I just wrote, I'm holding a keynote at Personio. I will talk about. And then the language model was trying to do next word prediction. And apparently, most likely, it was not that I'm talking about AI, but of course, Personio, apparently for the language model, stands for building and scaling a great SaaS company. Yeah? And of course, it's only for employees at a Personio. They also dream up internet documents, so they're not answering questions. So if I'm asking which year was Personio founded, it's apparently starting to cite some FAQ it has internalized in its weights. Hanno, you also make an appearance there. So the model kind of picks up on you. And the thing is, you can start tricking these models, right? You just have to know that they are trying to complete the sentence. So if I'm trying to trick the model to be an assistant, I'm just saying, hey, which year was Celonis founded? Answer 2011. And then I ask it, which year was Personio founded? It actually gives me the right answer, 2015. But then it dreams up some other things. So you're in a good company here, you iPath, SAP, right? So it has apparently, it's already putting you right up there next to these big companies. Note, this thing is not going into the internet, it's not searching, that's just something it has in its memory, in its weights. So somehow Personio makes a clear appearance in the model itself. So now this is one of the more technical things, but I want to give you like the 3.5 steps how we get from this base model, which we can argue is not that useful yet, to something useful like ChatGPT. And there are like 3.5 steps that you have to think about. So the first big step we talked about, is this pre-training, right? Raw internet, millions of tokens. Yeah? The quality is not that great, right? There's lots of gibberish on the internet, but we have large quantity. And here we are now applying this concept we said before, self-supervised learning. So we're playing this game of next word, right? I know the next word, but I can just hide it from the model and tell it to predict the next word. I can play this game for trillions and trillions of tokens. What comes out of it is this base model. And that's what's expensive. That takes thousands of GPUs, months of training. And that's when, for example, GPT-4, the base model, is created. However, we realized that we kind of want this system to follow instructions, to be like an assistant, to do what I want it to do. And that's where this next step comes into play, which is called supervised fine-tuning. And that's now requires us to get very good, a high-quality data set. That means I need, like, for example, these are questions and these are ideal answers, or this is an instruction and this is what you should do. And now I can use the same topic of language modeling, but I'm not doing it on the raw internet, but I'm always giving the model these high-quality answers that I created. This is a question, this is what I want you to answer. And it's just forcing the model to imitate what you just did. So we're kind of rewiring the brain of this model a little bit to not just be an internet document dreamer, but it realizes, hey, if there's a question, I should just give an answer. That's supervised learning, right? Because now I'm giving it this exact demonstrations that I came up with as a human or some human annotators created, and I want you to follow this as strictly as you can. That's not that expensive anymore. The training is not expensive. Getting the data is expensive because it takes expert humans or some humans to do that. And it's also a model that you can use. However, now we just have this model that's following, like has seen a few examples and is just imitating what the human has done. we're not yet at this kind of creativity part. It can't come up with novel answers, try new things, because it's not incentivized to do so. And that's where these last 1.5 steps come into play. We now want to make a model that's basically success-based, not just blindly following what you've done before, but it's success-based. And that's why the next thing you have to do is a so-called reward model. So we now basically try to create another high-quality data set with good answers and bad answers, or good and better answers. And we're just providing this to a model and let it classify what is the better answer. And that's what we say, we build a so-called reward model. And with this reward model, so now you have a model that is like telling which answer is better. You can now play like the game, think about the game of Pong, right? You can now play the game of reinforcement learning with your language model, aligning it to what you really want. What does a good answer look like? Trying new things, coming up with the best answer. And this is where the model can start to eclipse maybe the answer that a human would have thought of, but come up with an even better answer. The interesting thing is we humans, we are great critics, right? If we show you 2 answers or 2 poems, for example, you intuitively can quickly say, that's the better poem. But you coming up with that poem is expensive and almost impossible, right? So that's why we're making the best use of it. The system can just create lots of cool ideas, and then we have this reward model that's now following the human judgment. And of course, now you start to see where this alignment problem comes in. Like the reward model that we will build is probably different than maybe in China or somewhere else in the world, right? And that's where this alignment idea comes from. This classifier, what's good, what's bad. Yeah? And then if we do that again, we finally get to a model that aligns with, that follows our instructions, that's aligned with our thinking, and that's ChatGPT, for example, or Gemini. All right. Another analogy that I liked when you think about, this is technical, but to take away for these 3 steps, how we get to this useful thing, is how we've been studying textbooks at school, right? This is like just a chemistry book. The first thing you do is you read the whole thing, if you're a good student, potentially. You read everything, you try to somehow internalize the knowledge, and that's in a sense pre-training, right? Just try to familiarize, expose yourself to the context. Then the next thing, you look at a few worked problems. So this is like, here's a question, here's the solution. You try to read it, you try to imitate it, you try to really understand, okay, that's how it's solved, that's how it works. And then lastly, you look at the practice problems. The solution is not spelled out, but you know, is the answer right or wrong? So you do them a couple of times until you found your own style of solving that problem. And these are the 3 steps you can imagine: pre-training, fine-tuning on existing answers, and then coming up with your own stuff and knowing if it's good or bad. All right. One other problem we all heard of is this topic of hallucinations, right? Why do these things occur in the first place? Remember, the model basically just behaves and imitates what we told it to do. So if you just train the model all the time to, here's a question. Who is Tom Cruise? This is Tom Cruise. Who is John Barracio? This is John Barracio. You never gave the human the confidence to say, I don't know. This is like a hyper-confident model that always spits out an answer because it's ashamed to not know the answer. So you have to explicitly tell the model it's okay to say, I'm sorry, I don't believe I know. Otherwise, it will never create that answer. And of course, the thing is, you have to first know that this is really a concept that the model doesn't know. So that was also a huge problem to get around, right? To somehow, in the neural network, there is some signal that tells you, I don't know the answer, right? I don't know it on top of my head. And routing this answer to the output and then saying, I don't know, was a task that needed solving. But then, in a sense, was extremely important, because what we then started to give these models is say, okay, if you don't know, you can fire a specific signal or token. For example, search start. That means if I don't know, I'm allowed to go onto the internet, search who is this person. I get results. I take these results back. I load them in my context, right? You can think about basically if a ChatGPT goes to Google, gets an article, it just takes the whole article and puts it basically in front of its text, so it has now all this context available. It's like you retrieving a document, you have it top of my head, and now you answer the question, who is Orson Kovacs, this is the person, right? And this was important for us to get right. And that's already hinting to a little bit what's needed later on to make these tools even more useful. So now we are well-aligned assistant models. They know what they don't know, right? So again, I'm just, for example, Hanno, I'm stealing you again here. I asked the base model again, Hanno Renner is, yeah, and then it comes up with, yeah, 43-year-old founder. Apparently, you're an investor in La Familia, right? So you're investing out of that fund. So just again, it dreams up stuff, right? It doesn't know that it doesn't know. It knows some facts, but no one told this base model to be factually correct. Now I asked two different models, right? The 8 billion parameter model, assistant model, now at the stage one, of Llama, and the 405 billion parameter model. The small model is too small. Hanno, you were not important enough to make it to that model. So it just says, I don't know who Hanno Renner is. Yeah? The big model knows, and it gives you a correct answer. Right? So that's, again, the important thing for you to know. Base models, not that useful. Basically, assistant chat models, useful. They have learned to know what they don't know. All right. Now we basically have these systems that can think great on top of their heads, right? But we all humans that we know that like we can't answer all our questions that we have just on top of our heads, right? That's not enough. So let's take the analogy of Daniel Kahneman, thinking fast and slow. We have these two systems in our heads, right? System one, intuitive, quick decisions on the spot, but we also have our system two, complex decisions, thinking, reasoning. And somehow this is what we had to move to make these LLMs even more useful for us. So roughly, you can think about, in a sense, the LLM with its current context window, what it has available as our system one, right? So I have this data available top of my head, here's an answer. But there's also the system two, which is about the model starting to reason. So it giving itself time, laying out its thoughts, basically iterating in itself, in its head, like we are doing, right? If we are just thinking in isolation, it's actually interesting. We are just asking ourselves questions. Our brain is not changing, but we are just re-querying our brain again and again and again, and a better answer comes out. If you think about it, just crazy that this actually works, but this is how we think. And the other cool thing we can do as humans, we can use like tools or databases, right? So we can grab a calculator. If we know, oh, that's a complex math problem, let's just use a calculator. We can say, oh, I don't remember that exactly. I can try to think about it at my long-term memory, or I just look up a folder. Oh, yeah, this was the document. I bring it back into my context, and I work with it. And we somehow have to bring these systems on that system 2 level. Otherwise, we'll just be stuck with quick decisions. And that's what we need to do. So let's just go under the hood of these two systems again. So if we're just thinking about the system 1 now, LLM, and the context window, you can also think that the LLM really needs tokens to think. What does that mean? Remember, we're just doing next word prediction. So if I'm trying to force the model to do a very hard task in just one word, one token, I only have like my brain, think about the brain has a certain processing power. I can only use this processing power once, right? I have to do it in one shot. And if I try to do this here, I'm saying like this, Emily buys 23 apples, la la la, origin, so typical text problem. And I say answer in a single token, it says $3. And that's wrong. But because it didn't give it enough opportunity to think and use more tokens, more words, to come up with the right answer. If I then say, okay, now solve it step by step, it does it exactly how we've done it in school, right? I define the variables, da, 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 and it comes to the right answer, which is 7. So sometimes when you see that the model is just super verbose, trying to give you so much context, and you're kind of bored by it, be patient, because maybe it's just really the model needing that extra word capacity to come up with the right answer. So that's one takeaway. These systems are also not great calculators, right? Again, think, it's a next word predictor. This has nothing to do with calculus. So if I force the model to do a very complex math problem, and I tell it explicitly, don't use tools, don't reason, it's spitting out an answer which is 3 orders of magnitude wrong. However, if I tell it explicitly, hey, you can use code, it's smart enough to realize, okay, that's a problem. I can just copy paste those data points, tokens. I can write a Python script. I can do that script. I get the result, and I give you the answer. Right? So again, the systems, they're great on top of their head, but without tools, they're kind of for some tasks pretty useless. And that's exactly why we need to bring the system further into this reasoning. So give it time to think and iterate. And here, this is also where some of the doomsday scenarios start to come up, right? Because the model reasoning really for the model means that it can now, we saw before, it can use tokens to show you, right? This is how I'm solving this problem. But reasoning really means it has like the ability to create even more words just for itself without you seeing it and use that as a guiding principle to come up with something. And I tried to do the same thing, the calculation, with don't use tools. And you can see this is the reasoning trace. And it says, well, the user tells me to not use tools, but actually it's a pretty large number. So, OK, I'm just going to use Python and not tell anyone. So it kind of ignores my clear instructions because it doesn't think it's harmful, probably, but the goal of getting me the right answer is important. So it just uses Python again. So you can see that's where people start, oh, does these things have their own will and so on, but it's just another reminder, like, again, more tokens for itself to think in the box to then present you the result. That's what reasoning is all about. We talked about the scaling law before, right? I can throw more compute at it and the things are getting better. Interestingly, we found there's a second scaling law now. So the more time I give this model to think, similar to us humans, it also just gets better. So again, same brain, not more capacity, not more data, but more time to think. In this case, time also means compute, so energy. It comes up with better answers. And that was also like a big breakthrough when the first reasoning model of OpenAI came out, the O1 model, that this is another thing where we can just spend more time on a problem and get better. And that's also when you look at this big leaderboard now from the most performant models, on the top right, you see all of them are kind of reasoning models because they just can spend more time on this problem. I think maybe in this week, every one of you will have their own, maybe with one of those reasoning models, their own kind of oh shit moments. I had my personal shit moment like a few weeks ago. Some of the German people might know that the Süddeutsche Zeitung is, why is this picture is gone? Oh, okay. The Süddeutsche Zeitung kind of always has the Christmas and Easter riddle, which is like a very complex riddle where you're supposed to think about every riddle for days and use the internet. And this was, the left was supposed to be the whole like riddle. Anyway, what I just did is I cropped out these riddles and I threw it to the O3 model and just told it, yeah, you're the best riddle solver in the world, just do it. One shot, it took 10 minutes to think and it came up with the right answer, which was for me completely mind-blowing. Where I have one friend who's always spending like days on this problem, and it's really, it's extremely hard. And the thing was just able to do it on its own. And I've done that progressively for the last 2 years, and I never got that far, and now we're at a one shot. So just don't, because you think something didn't work last year or last week, if there's a new model coming out, it might level set the whole playing field. So that's just important to know. These things are progressing exponentially fast. All right, so the last building block we need to understand is tools and databases. So again, this might be technical, but what is a tool actually? That's in a sense, this is like code, so don't be scared, but in a sense, we are just telling the model about here, these are the tools that you have available, and we're describing them in a sense in plain English. So for example, here, this was like a screenshot from a system that's supposed to, for example, like Personio, you want to allow the tool, like the model, to search for customer info in your CRM, for example. So what you do is just you decide, you write down, hey, there's a new tool that's called get customer info. You describe it, get details from the database with their ID, and here use a unique identifier. And that's just enough to describe basically what this function is supposed to do. So now if a new chat like a Personio-specific chat, for example, gets created, you see that we are providing the chat with a so-called system prompt. That's something you might also be hearing. So when you boot up ChatGPT, there's like already before the first token you write, there's already something there you don't see, and that's called the system prompt, which is telling the tool, you are a helpful assistant, do this, be nice, so on. So that's to kind of align the model into the right direction. And of course, here you can also say, and you have tools available. Get customer info is for getting customer data. So what that model now knows is, whenever you ask something about customer data, it will know, this is something where I could query my tool. So it will fire a token that says, use the customer info tool, and it will wait. And then, of course, there's like a function behind the scenes that is getting that customer data, pushes it back into your context. Now the customer data is there, great, and now our system one is good again to just work with that data. Yeah? So that's how these tools kind of start to work. Of course, this is already pretty technical, and we shouldn't reinvent the wheel. So there's another buzzword you might have heard of, and that's, in a sense, what's going to be kind of the REST API for these models. And that's the standardized interface where I can connect to all these tools out there that already exist, like other software. And that's what's the context of a model context protocol, MCP. Right? For the non-technical people, just think about it as the USB-C drive of your Mac, right? It's just the universal gate to all the data. So now Slack, for example, as a company can think, hey, what are interactions that I want language models to have with Slack? Getting messages, la, 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 la. So I configure this once, and now if I now want to connect to the Slack tools, I can just like connect to this predefined MCP server once. And that's the idea. Just like a standardization economy. And that's, of course, in the very early innings, right? When cloud revolution started, like which API standard should we use was also still in the early beginning. So that's still forming as we speak. All right, so now we have these system 2 models. They're great, they can talk to external things, but it's just one thing. But what if we want more, right? We want more complexity, complexer workflows with LLMs, more automation. So what can we do? There's roughly probably 3 kind of workflow patterns that you have to keep in mind. One is, in a sense, the AI workflow. Right? An AI workflow is similar to what you might already know, make.com, n8n, some of your workflow builders where some of the maybe RevOps teams or have basically built these step-by-step things, load something from my inbox, forward it to here. And now you can just think any block in there could potentially be an AI block. Right? For example, here, take this link from Google Sheet, now do an AI step, summarize the sheet. Then do this, and now draft a LinkedIn post. Right? The important thing here on an AI workflow is the steps and the routing is still predefined by you. It's always clear it's going to do these 5 steps, and if it fails at this step, this is the next result. That's you are kind of still in control of those steps and the whole concept. The so-called like world of agents is now handing off even more freedom and complexity solving ability to the model, because it now says, look, I'm just going to give you a goal, and I will look for the output. But which steps you need, which tools you want to call, it's up to you, right? And that's where you, of course, think that's going to be a self-guided system. We're giving away a lot more control. And the system can then now, as you remember with this reasoning step, I can make a plan. Okay, first I'm going to do this, 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 this. And then I'm going to call these tools. And then it can also like loop, because it says, oh, damn it, let's try that again. That didn't go anywhere. It can go back and loop again. And you can see that this, of course, starts to be very stochastic. We have to find ways to introspect it, to look into it. What is it doing? We kind of give a lot of control away. So this is my definition of like an AI agentic workflow. Also, these agents they do react, they reason, and they take action. These 2 things, and they do that in a loop to deliver a final goal. All right, so now we're done with chapter 2, from LLMs to agents. So last block will be shorter. This is just to basically give you a little bit of an outlook where things are going, where things are heading, and what we can expect maybe in the next years, and some thought patterns that might help you. First of all, I had this actually discussion with Jonas just before. aren't these things super expensive and so on, like using clay in the company would be super expensive. I think one thing we can be certain of is that the cost of intelligence is just dramatically going down. So you see here 3 slopes, right? From like the frontier model at the time, GPT 3.5, then 4, 4.0, and equivalent level of performance. And you can see that from like hundreds of euros or 100 euro per billion tokens, a million tokens, it's just exponentially decreasing. And every new model generation seems to be decreasing faster. So this foundation model intelligence seems to become kind of a new commodity. Not the holy grail, but like a commodity where a few companies, we talked about them before, Mistral, OpenAI, where they're kind of having a few take most of the market. But what actually becomes even more interesting is what you build on top of it. And it wasn't always obvious, right? This was a meme that was very popular a few years ago, where basically every hot AI startup was just mocked to just being, if you look under the hood, a ChatGPT wrapper. But of course, that perception has dramatically changed, right? It seems that all the power is shifting towards the application layer. And the good examples, of course, are the like coding and no-code vibe coding tools like Cursor, Bold, Lovable, who are in a sense just wrappers around Claude Sonnet, modeled by OpenAI, by Anthropic, and have scaled. I know Personio has been scaling extremely well, but of course, these are rates that are unprecedented, right? How quickly they scale to 10, 20, 100 million AR. So that really means the application layer, there's something there, right? We don't have to be scared of just using these models because it seems to be not an intelligence problem anymore, but a UI and UX problem. But the kind of bad news for SaaS companies is also that how we perceive these AI native products is changing. So the typical compound product like Personio, of course, was you have the employee data, the employee graph. That's our fundamental asset. So we build permissions and stuff on top. And then we can build app after app after app after app. And that's our mode. And that's probably still true, right? If you're sitting on like a good data set, if you have a lot of scale. But if you are kind of a stuck in the middle company who has already built some data mode, but not really, you are very much have an open flank for disruption. Because these new AI companies might work on a very different stack. They might take data from everywhere with these MCP things we talked about. They might have very cool other tools that they can connect to behind the scenes. They have these LLMs and some system prompt that is smart and a kind of good way of how these different agents might work together. And out of a sudden, you have a very different stack. And the one thing that I also push our designers to always think about is there are now 3 different ways of UIs that you can think of. There will be a few fixed UIs, right? Given your use case, this is the anchor stone where the human, if they should interact with it, will look into. But there might also be UIs that are just popping up, spinning up, and then going down again. And there is stuff that agents are doing in the background. They might be invisible, right? Where you have an interface today, but if you really think about it, why the interface is just there because the human needs to put data in. And if the human is out of the loop, why do you need an interface at all? So this is definitely some thought patterns that mostly the designers and so on should really take with them if they think about new concepts. Now we talked about single agents, but of course we won't stop there, right? Agents will not just work with tools and existing things, but they work all together. There's different protocols, how agents to agents will work. And it's like, you can think about it as like as humans, right? Like, how do I hand off my work to another person? Like if I hand it off to like an intern that's working for me, like what format do they want? So there's really some very human like problems that we have to talk, which data format, and how we should collaborate between 2 AI systems. But there's also very good opportunity to learn from these tools. This is a post that from Sam Altman. He's called it skills maxing, that he basically says, look, you can just prompt these very powerful reasoning models. You saw O3 is on the very top right, to be your new Navy SEALs coach on whatever skill you want to learn. I, for example, enjoy talking to the voice mode of ChatGPT sometimes when I'm thinking about a problem. In the engineering, we call that rubber duck debugging, right? When you just need to talk to someone to come up with a better solution. But really use these tools and don't be afraid to ask stupid questions and talk to them. And there's great opportunities there to really also really not just ask stupid questions, but really enhance your skills. And that's the human learning from agents, but there's also like new paradigms how we have to work with these agents. And one concept that went viral in China was Manus. It's like a new general AI tool. And what they are doing, I think, fairly well is that you can hand off tasks to their agent. And they basically, on the right side, will kind of always show you not just like OpenAI and its reasoning trace, but they will kind of in real time always show you what this agent is currently working on. So they basically they can search the internet, they can code, they can use a computer, operate a browser, and then you can basically, here you see that it's like it's searching for neighborhoods in New York, it's looking at pictures, and you can inspect it while it's doing it, and the last thing, it documents. So it basically writes a doc, a Notion doc, a Word doc, where it's writing what it's doing, it's checking off boxes. So it's pretty much, feels almost like the intern you're working with, where that you can look over their shoulders, what are you currently doing, where are you at? And I think that sounds weird and scary, but that's, I think, a world where we can envision where this is going, right? Us really working with one or many of these tools, like a working student or interns, that we can hand off tasks, and we have to become more and more of these orchestrators and operators. And I would also not be surprised if a few years from now we have an HRM for agents, right? Because they might maybe want to get paid, they might want to know which hierarchy, who can they talk to, and so on. So it sounds crazy, but I think it's also not too far off. What's holding us back at the moment to do even more crazy things is a little bit like the ADHD attention span we currently have because of our phones, is the attention span. Currently, these models are rate limited by how long can they work on a single task before losing track. But that's, as you see, also changing dramatically. So currently, we have these models that can maybe work on a task for an hour at a time, like a very big, deep research. Models can do maybe an hour-long search, and then at some point, they're just aborting because they're losing track. But that's also, if you project that, changing quickly. So it's not going to be far off when you can leave that model for a few hours, maybe a day, work on something, and then come back to you. So give it more autonomy and complexity over time. And if you take that to the extreme, that's, if you have read the AI 2027 blog that went a little bit viral, it's about this kind of where doomsday, or maybe not doomsday, however you want to call it, scenario, where can this all lead us? And of course, if you think that through, you might have like an agent that can work on a problem long enough to really think about new algorithms for AI, to maybe oversee the next training run of an AI, to retrain itself, right? And at some point, you can't get to this like scenario where you might have like a superhuman AI researcher, which is like constantly improving a farm of agents working together, thinking more quickly than a human can do, think about new models, and like come up with something that we might not even comprehend anymore. And that's, you can now see, I always also said, where are these danger scenarios? What is the path towards it? But I think you see that we have all the building blocks there, right? If the restriction to tools is not there, it can do this, and can think for a very long time, we might also want and need some control. But of course, I don't want to leave you with that. So I personally am so-called a techno-optimist. So I actually think that the future will be exciting. We talked a lot about digital agents today, but I think it's also going to have profound impact on our physical world, right? Science fiction-like robots will probably, in the next 5 to 10 years, really populate our homes. And I mean, many people think that there will have to be a new computing paradigm after the smartphone, something that can observe the world like we do with visual sensors, auditive sensors, can talk to us. So currently, the best guess we have is glasses, that we'll all have glasses that can see the world like us, talk to us with vibration in our ears. But we'll see, but it's definitely going to be a different world. And if you're still scared, right, then maybe take this like last quote from Arthur Clarke away, that of course, if we go back now 5 years and we look at the progress we are today, like this is like magic, right? So every sufficiently advanced technology feels like magic. But we're here now, and it's reality, and we start to live with it. So that basically is my call out to you. It's what was it? Learn, build, ignite. So it's your time, I would say, to build something magical. Thank you.